Good day to everyone. This is Earthquake Engineering Geology 149, and this is the first lecture which comprises the basic concepts, and we will be also tackling the landmark cases through an external lecture. Now let's start with the plate tectonics of earthquakes. You have three main types of plate tectonic boundaries that involve earthquakes. First is the subduction zone. And under the subduction zone, we have four subtypes. First is the shallow interplate thrust, and this is basically about the slippage between the two plates, right? So you have the two plates are subduct that are involved in the subduction, and they tend to stick together a bit, right? Until you accumulate enough stress such that the downgoing plate and the overlying plate slips out of each other. The other type is the shallow earthquake in the upper plate. All right, so the overriding plate is trying to accommodate the movement, so it undergoes internal deformation to make room for the downgoing plate. The next type is the shallow to deep earthquakes, all right, within the downgoing plate. All right, so this is mostly involving the also the internal deformation of your downgoing plate as it subducts. And the last subtype is the earthquakes located at the seaward side of the trench. Right, so this involves the flexing of the downgoing plate. Now you also have your continent to continent collision zones. These are two large land masses that are essentially just colliding like two cars that are crashing down to each other. And what happens is there isn't much room for them to go. So what happens is they get squeezed, they deform, they fold, and they thrust upward and form mountain ranges like the Himalayan mountains. And then the last important plate tectonic type is the transform boundaries, where you have plates that are just sliding past each other. Okay, so instead of colliding like the subduction or the collision zones, you just have plates that are uh, sliding past each other. Okay, they're more or less moving parallel, right? This is just an illustration of the convergent boundary and the uh, involving oceanic to continental subduction zone in the top figure. You can see here, this is the oceanic crust that is uh, moving or that is subducting. And then you have here the continental crust that is overriding, right? And then the second figure is your continent-continent collision zone. You have two continental crusts that are merging or colliding, and in the middle you get a mountain range. Now let's talk about terminologies involving faults. A fault is a fracture or a zone of fractures, all right, in which displacement has occurred. So a fault can be either a single line of fault or it could be composed of multiple fault ruptures that are grouped together. All right. And then the other term is the fault length, right? So this could mean two things. First is the total length of your fault or total length of the fault zone. Or this could also mean the length that is associated with a particular earthquake event. So note that each earthquake event typically just involves movement or displacement within a portion of the fault. Okay. So for example, I think the Bangi fault in Ilocos is approximately 200 kilometers long, but in the event of an actual earthquake, it's very unlikely that the whole 200 kilometers will actually move. It is more typical for just a portion of the fault to undergo displacement during an earthquake. Okay? So length is important because it has implications on the magnitude of the earthquake, which we will be discussing later in the other lectures. Another term is your active fault. Okay, not all faults that you can map are active faults. Okay, so active fault is a fault that can still produce an earthquake, and while inactive faults are faults that are basically highly unlikely to produce an earthquake. So how do we define an active fault? An active fault has movements that are as young as 10,000 years, okay, or basically Holocene age. And we can determine the age of a fault movement or an earthquake based on different sources. You can base it on written records. Like in the Philippines, we actually have a 400 years of written records courtesy of the Spanish friars who are actually who have documented the events in the Philippines. Okay, if you're interested in reading about that, you can search the chronology of, I think the name is Sadara Maso. Okay? He's a Spanish official who compiled all the 400 years of earthquake history and geology in the Philippines. And then you also have earthquake records from your seismographs or accelerographs, courtesy of FIVOX and also USGS. All right. Okay, so you can access earthquake records from the FIVOX website and also the US Geological Survey. They also compile the earth. They also maintain a catalog of earthquakes that have occurred uh, all over the world. Another basis of your age of earthquake is your fault crunching. This is literally, or this literally involves going to the trace of the fault. So you go out to the field, you look for the fault, and then you dig, you dig perpendicular to the trace of the fault, and from there you can see the cross-cutting relations and the stratigraphy. Okay, so basically, if your fault is cutting through your Holocene sediments, Okay, so it means it is younger than your Holocene sediments, and therefore its last movement is within 10,000 years, and therefore it might be an active fault. And then you can also do absolute age dating, right? Like using quartz. I think quartz luminescence dating. Quartz luminescence dating is basically about dating the taking a quartz sample from your soil and looking at when was the last time that the quartz sample has was exposed to light. All right. There are also other methods like carbon 14 dating, right? Now we have different types of faults, and as listed below. Now let's discuss them one by one. You have your Strikeslip fault, which, as you can see in the figure, all right. So you have a movement that is parallel to your strike. So this is your before, and after the movement, your landmass has displaced parallel to the fault trace. Now, just to clarify, a transform fault is essentially just a strike slip fault that is humongous, like it is in the size of plate boundary dimensions. So we're talking here about hundreds to thousands of kilometers in length. Now, normal fault is when your hanging wall is moving downward, okay, with respect to your footwall. This is a tensional or extensional regime, so your area is extending, and to accommodate the extending movement, your hanging wall has to go down. As you can see in the figure, the before you have your footwall on the left and the hanging wall on your right. And during your earthquake, your hanging wall displaces downwards, and in the process, it disturbs the ground immediately beside the fault. And then after the earthquake, the ground beside the fault collapses or gets disturbed, gets fully disturbed. Okay, so it might undergo local thrusting, as you can see here. Now, reverse fault is a fault in a compressional regime. So your ground is compressing laterally, and for that, the hanging wall has to move upwards to accommodate the movement. You can see in the figure, in the before figure, your hanging wall is on your left and your footwall is on your right. And then during the earthquake, your hanging wall moves towards the left, and it also gets thrusted upward. Okay, so it rises. It essentially rises. And typically your soil or your ground, which may be composed of soils, they normally can't really sustain a high angle or a high relief. So they undergo slumping, as in the after, as shown in the block diagram in the after the earthquake. Okay, so this is basically just your ground adjusting or responding. Okay, after it was after it was thrusted. We also have a subtype of reverse fault called a thrust fault. And this is a fault that has a dip angle of 45 degrees or less. Okay. Another type, or rather, this is just a descriptor. A blind fault is just a description for a fault that has never reached the ground surface. Okay, so meaning you might not see the actual rupture of the fault of a blind fault. Okay, you won't see the actual rupture here. Okay, you might just see an anticline. Okay, so what happens in a blind fault is the fault or the underlying geology is ductile, meaning it can easily bend or it can easily bend a lot without breaking. Typically, ductile formations are your sedimentary sequences or alluvium, right? And the thing with blind fault is, of course, it's difficult to map because it doesn't have that classic ground rupture. Your it it doesn't have that classic fault rupture that you can see on in the surface, and it's difficult to know which anticline involves an active fault. Okay, normally what we only get to identify or know if the blindfold is active or not is after an earthquake. Okay, and this is what happened in the Negros earthquake years ago. I think it was in 2014 or 2012. Okay, so you have a blind fault. A blind thrust fault is just a thrust fault that is blind. So it doesn't have a surface rupture. Other fault descriptors, you have your longitudinal step fault or your step fault. This happens when your main fault undergoes branching into several parallel subsidiary faults. As you can see in the top right figure, these are your subsidiary faults, and somewhere down is your main fault that has sprouted into several smaller faults. You also have another descriptor called dip slip and oblique slip, right? You have a dip slip when the displacement is only occurring on the dip direction, meaning the slippage is only involving a single direction, which is in the direction of the dip of your fault. So you can have a dip slip normal fault. You can also have a dip slip reverse fault. Another descriptor is the oblique slip fault, and this involves slip on dip and strike directions. Okay, so more or less the movement is diagonal with respect to the strike or with respect to the dip of your fault. Now let's talk about the instrumentation or observation of earthquakes. There is what we call a seismograph, or the instrument which records ground motion, right, due to seismic waves. Now note that just to avoid being ambiguous, all right, there is a seismograph that is meant for earthquakes, and there is also another type of a seismograph that is used for geophysical seismic surveys. So their name is the same. They are both called seismograph, but you typically need two different types depending on your intended purpose. Now, a seismogram is the actual recording done by the seismograph. And then another term is your accelerogram, which is just a type of a seismograph. An accelerogram records acceleration versus time, while an accelerogram is the actual record of your accelerogram. This is an example of an accelerogram accelerogram recorded by an accelerogram. As you can see on the figure on the right, this you have three sets of squiggly lines. This is from the 1971 San Fernando earthquake in California, USA. So this earthquake is important for the event involving the liquefaction failure of the San Fernando Dam. Okay. This is one of the few known cases of liquefaction failure on an embankment dam. What happened here is San Fernando Dam was composed of mainly sands, which was prone to liquefaction. And after that event, there was a total division of the design of embankment dams. So after that, the design of embankment dams started favoring the use of impervious cores and rock fills. Right, so let's go back to the accelerogram. The top portion is a record of acceleration through time. The middle portion is a record of velocity over time, and then the bottom is displacement over time. Now, the main recording here, or the actual recording, is just the acceleration over time. Now, using mathematical integration, you can just integrate acceleration through time, and you can determine the velocity, all right, through time. And then further integrating velocity, you can obtain the displacement. Now, let's have a brief crash course on how to read an accelerogram. Okay, this is still the example shown previously. On the top portion is the acceleration versus time. And from here we can determine the important parameter, which is the peak ground acceleration, or basically the biggest acceleration that the ground has experienced. What we do here is we just look for the biggest jump, or the biggest amplitude, or rather the biggest jump in acceleration. Okay, so this is a big jump. This is also a big jump in acceleration, but this is the biggest one. So once we have found the biggest jump in acceleration, we just measure it with respect to 0. All right. Now this peak ground acceleration is approximately 250 centimeters per second squared, right? Now you can also have a peak ground acceleration in the negative y-axis, so that's perfectly fine. So you're just in here, you're just concerned with the absolute value of the jump in acceleration. Now the same method is done in the peak ground velocity. So we just take the biggest jump in velocity and then we just take the absolute value of that. So in here we have 30 centimeters per second. And then for the last one, the displacement, you can get the peak ground displacement from the biggest jump in displacement here, which is approximately 20 centimeters. Or I mean less than 20. It's actually 14.9 centimeters. Now let's talk about seismic waves. Now, in the event of an earthquake or the fault rupture that generated the earthquake, there are various seismic waves that are generated. First is the P wave, which is a body wave. Okay, a P wave is compressional, and this is the fastest moving wave. All right, and all right, so this is the fastest moving wave because solids and liquids have a high compressional moduli, meaning that this simply means that solids and liquids respond fastest to compression disturbance. Okay, and P waves are readily resisted by soil and rock, since so therefore in their effect in terms of earthquake damage is typically minimal. Another type is your S waves, or which are also a type of a body wave, and they involve shear displacement. And S waves only propagate in solids. Now note that soil and rock have low shear resistance, so they tend to displace a lot when they are subject to S waves, and therefore, so big displacement, which can result in uh, a high degree of disturbance to your structures and buildings and houses. So S waves can produce a lot of damage. And then you also have your love waves and Rayleigh waves, which are a type of surface wave. A love wave is just essentially an S wave, which is oscillating perpendicular to the direction of propagation. Okay, so it looks like a snake. It's like a snake. Its movement is similar to that of a snake, which you can see later on. And then your Rayleigh wave is a surface wave which is moving in a reverse rolling motion. Now, surface waves like love waves and Rayleigh waves are the most destructive for two reasons. First reason is that seismic waves tend to. First reason is that approximately 60 to 70% of seismic waves are in form of surface waves. So meaning almost two-thirds of the energy generated by the fault rupture is transmitted via your surface waves. Second reason is that surface waves just concentrate on the surface. So they travel just near the surface. They travel in the interface between the ground and our atmosphere. So as a result, the waves are in close contact with the surface structures like buildings, houses, and they receive a more or less a direct hit of the seismic wave. Now, in the perspective of engineers, it's not important for them to distinguish between the different types of seismic waves. Another reason here is that there are various empirical and there are a lot of methods to directly or calculate the effect of an earthquake, all right? Like the peak ground acceleration, peak ground velocity, peak ground displacement, resonance frequency, which are due to seismic waves, all right? But since engineers are just concerned with the numbers, they don't really need to know what types of seismic waves are affecting their site. They just need the numbers. And you will see later on why. Alright, another note here is that peak ground acceleration is mostly influenced by shear waves. Alright, and that distance is greater than twice the thickness of Earth's crust, which is around 10 to 140 kilometers distance. The surface waves will produce the peak ground motions. Now, this is just a visualization of the different types of seismic waves. On the upper left is your P wave, which involves compression. As you can see here in the square, which is undergoing compression when it is hit by the wave. On your upper right is your S wave or your shear wave. Okay, so it's undergo sheathing. So the ground is moving up and down as it propagates. And then the bottom left is your love wave, which is going sideways. All right, so it's moving sideways as it propagates. So it looks like a snake. And then the rally wave is just a type of an S wave, but most of the movement is concentrated on on the surface. All right, so again, if you would look at the S wave, the movement is going up and down, and it involves the whole body. For the rally wave, it only involves the upper part of the body here. Now let's talk about magnitude of an earthquake. Magnitude represents the measure of energy that is released during the earthquake. And this is typically calculated using the amplitude of displacement or other indicators as you will see later on. Now you have three main types of magnitude scales. You have your local magnitude or M sub L. You also have your surface magnitude, which is M sub S. And then you also have your moment magnitude, which is M sub W. Now, what's the difference between these three different scales? For the local magnitude, we calculate the energy from the amplitude of displacement as measured by a wooden Anderson seismograph. All right, and this seismograph is typically calibrated for a 100-kilometer distance from the epicenter of an earthquake. Now, if the earthquake occurred like 50 kilometers or 1,000 kilometers from the epicenter, there are correction factors, all right, in to to normalize the values to a 100-kilometer distance. Now, there is a formula here, but I won't be discussing it in detail. Okay, the important here is just to know the differences in the methodologies of these different magnitude scales, and to also know the limitation of each scale. So again, local magnitude is all about the amplitude as measured from a specific type of a seismograph, which is a wooden Anderson seismograph. Now, the surface magnitude, or M sub S, is based on the amplitude of your maximum ground displacement. So in here, you have to know the actual ground displacement after the earthquake. Okay, so this can be measured using seismographs, and there are a lot, or there are different types of seismographs that can be used to record the ground displacement. Okay, so the advantage of your surface magnitude is you are not restricted to a wooden Anderson seismograph. And the other advantage of your surface magnitude is it is quite uh, accurate when you are dealing with moderate to large earthquakes. Although the limitation of your surface magnitude is, right, so when you have a large earthquake like magnitude 8, all right, after magnitude 8, like magnitude 8.1, 8.5, magnitude 9, all right, so beyond magnitude 8 earthquakes, the relationship between the size of the earthquake and the maximum ground displacement becomes non-proportional, or it means that after magnitude 8, the value of maximum ground displacement tends to plateau. So it flattens. Okay, it flattens to a certain value. Okay, so a bigger earthquake, or an earthquake bigger than 8, might not necessarily have a much bigger ground displacement compared to a magnitude 8 earthquake. Okay, so the surface magnitude scale is not so useful when you are dealing with earthquakes that are larger than magnitude 8. And this is where the moment magnitude, or M sub W, comes into picture. The moment magnitude scale uses fault rupture displacement. So you have to measure the actual fault rupture, and you also have to measure the area of the fault plane. So what happens here is we are measuring those two parameters in order to calculate the seismic moment. Okay, so we're sort of dealing with the momentum of the whole Earth with the whole fault plane. Okay, And from here, we can actually calculate or approximate the total energy that was released by the earthquake. Okay, so moment magnitude is a function of the displacement and the area of the fault plane. So the implication here is that you can have you can have two earthquakes with this with similar fault rupture displacements, but they might have different areas, different sizes in terms of area. Okay, so in this case, the earthquake event with a larger area or a larger fault plane area will have a bigger moment magnitude, even if they have the same fault rupture displacement. All right, so that's the advantage of your moment magnitude scale, is that it accounts for the actual size of the fault plane. Okay. Now, in terms of convention or standards, the most widely accepted or adopted scale is the moment magnitude scale. Now, just to see how the different scales relate to each other, we have here a plot of your moment magnitude in the of different magnitude scales versus your moment magnitude. All right, so the x-axis is the magnitude using different scales like local and surface magnitude scales, and then the x-axis is your moment magnitude. All right. So you have here a straight line, a straight and solid line. This is your moment magnitude. So moment magnitude versus moment magnitude is 1:1. All right. So a magnitude 3 in moment magnitude is also magnitude 3 in moment magnitude. So this is our reference point. Okay, so moment magnitude is considered the most accurate scale. So this is your moment magnitude scale line. Now, if you look at the uh, local local magnitude, so it is more or less consistent with the moment magnitude until you hit magnitude around magnitude 5, right? So after magnitude 5, or magnitude 6 rather, sorry. So after magnitude 6, your local magnitude scale drop into small starts to drop. Okay, so it starts to measure smaller values. Okay, which is due to the limitation of the method. Okay, so the main limitation of your local magnitude scale is that uh it it depends on a wooden Anderson seismograph. And another limitation is that it doesn't account for the size of the fault plane that has displaced. So remember that when you are dealing with large earthquakes, the displacement starts to plateau. Okay, when you start to have increasingly large earthquakes. Now, if you compare the moment magnitude line versus your surface magnitude, okay, so the surface magnitude is more or less consistent with your moment magnitude until it hits around magnitude 8. Okay? So at magnitude 8, the surface magnitudes is, since it doesn't account for the area of the earthquake, it is unable to properly measure the total energy of your earthquake. All right. Now, the last part here is your earthquake intensity. Earthquake intensity is another measure of your size of earthquake, but this one is based on damage and other secondary effects like earthquake-induced landslides, liquefaction, ground cracking or ground rupture, and also the level of shaking that was felt by the people or the residents. Now, note that you can easily expect a large amount of discrepancies when you are talking about when you're talking about the effects of an earthquake in an urban setting like Metro Manila versus a rural setting like far-flung areas of Laguna or Batangas. So, so you can easily expect. So intensity is really just a, let's say, a qualitative or a descriptive measure of your earthquake. Okay. Although in sometimes intensity can be useful in estimating the energy of your earthquake. And there are studies done by FIVOX, all right, particularly by Bautista and Oda, where they used the earthquake intensity to estimate the earthquake magnitude uh, during the Spanish times. Okay, so I will be discussing that paper later on. All right, so intensity, if you were to look at intensity on an objective perspective, intensity is a function of your size of earthquake, the distance of your earthquake, as well as the local and regional ground conditions, and also the type of structures that are in the area. This is an example of involvement of different factors that can affect the intensity of an earthquake. This is the 1985, sorry, going back, the example here is the 1985 Mexico City earthquake or the Michoacan earthquake in Mexico City. All right, for context, this is a very distant earthquake. So the earthquake was like 350 kilometers away from Mexico City, which is actually quite far. Because if you will look at the 1990 Luzon earthquake, the Luzon earthquake affected areas within 200 kilometers. And 200 kilometers is already an exceptional. Okay, so an earthquake affecting areas within 200 kilometers is already exceptional. So 350 kilometers is actually an amazing feat for an earthquake. Now, what happened here is the earthquake had a large magnitude, and when you have a large magnitude earthquake, this can involve a lot of long wavelength body waves, which can travel very far. So you can imagine a long wavelength body wave is like a man that is just ju- is making long jumps with every movement, while a short wavelength body wave is like a midget that is taking a lot of steps to travel a particular distance. So long body waves, all right. So they are like jumpers. They jump large distances, so they can cover large distances without losing a lot of energy. So they traveled 350 kilometers without losing a lot of energy, and eventually these body waves eventually reach the Mexico City, and it encountered thick softly deposits and a basin geometry of the sediments underneath Mexico City. So for the sake of discussing the history of Mexico City is an ancient Aztec city. Okay, I think it's called Tecno, and it was a city in the middle of a lake. Okay, so the whole city is un, is underlain by lake deposits. So the soft clay deposits are prone to amplification by seismic waves. So you can imagine an obese or an overweight man with a lot of fat. If you push the man a little bit, the fats of the man can jiggle really, really easily. So you're sort of you can easily induce a lot of movement with soft materials. And also the basin geometry also helped trap and accumulate the seismic waves within the area. And further, the mid-sized residential buildings, which are approximately 6 stories high, resonated with the seismic waves, meaning the height of the buildings synchronized with the seismic waves. And once you get resonance, what happens is that your building will just keep on swaying, shaking, will just keep on shaking. And with each shake, the swing becomes larger and larger. So you have a building that is swinging more intensely with each swing. So it is resonating until the building just collapses. All right. So resonance is more or less a guaranteed destruction for a building. Now, part of this lecture is the landmark earthquake cases, but I think this is better discussed by the lecture of Dr. Kevin Franke by the Brigham Young University, and I have provided the link for you to follow. Okay, so all you have to do is just watch lecture 2, and there are other video lectures in that series which are not required at the moment but are highly recommended. So thanks